we are going to look at a bunch of different word problems and situations where sinusoidal graphs can be used to model. In this question here, it's the depth of a water because tides come in and out. They can be predicted, and so an equation can be made, and these equations are going to be important because the depth of water has implications for ships coming in and things like that. So this equation, the equation is given to us. This is the easiest type of word problem because the work is mostly done for you. Because the equation is given where d of t is the depth and t is in time in hours after low tide. Sketch the graph. So we're going to use our dab C to sketch this graph. When I draw my axes, I can already see that my center line is going to be at 13.7. So if I choose that somewhere along my y-axis, now I've sort of set a scale. My amplitude is 4.5. So if I go up 4.5, which would be approximately that far, and down 4.5, I can label my maximum's at 18.2. My minimum is at 9.2. I now use my b value to find my period. Now, in this case, the b value is 0.16 pi. Remember your formula. Your period is 2 pi over your b value, so it'll be 2 pi over 0.16 pi. You go to your calculator, type that into your calculator. And I believe it's 12.5. Double check that. Yes. So we can mark one period somewhere along our x-axis and divide it into 4 equal sections. Label those 4 equal sections. What's half of 12.5? 6.25. What's half of 6.25? 3.125. And then this one will be 9.375. This is a coast graph. A coast graph normally starts at a maximum, but there's a negative in front, so it's a negative coast graph, and a negative coast graph starts at a minimum. And once you know where it starts, you just have to hop minimum to center line to maximum to center line to minimum. Since there's no shift in this one whatsoever, we can draw this as the final graph right away. So we've got our graph, and now we can answer some application questions. They've got a big ship, a bulk carrier, needs at least 14.5 meters of water to come into the dock safely. For how many hours per cycle can it be safely in the harbor? So we look back at our graph, and if I think about 14.5, put it on here in purple, 14.5 would be about here. Can you see that only in this section here that the water is deeper? So we need to find what time is it here and what time is it here. So first of all, we're going to find out how we can use a graphing calculator technology to help us with this. So what we're going to do is we're going to type this equation into our graphing calculator, and we're going to see if we can have this green graph appear the same as we have it on our graph. So if you take out your calculator and you go to y equals, we'll type in this equation, negative 4.5 cos 0.16 pi times x, bracket, plus 13.7. Make sure your calculator is in radians because we're using radians within the question. And right now, if I hit graph, that's what I get. Nice. And if you hit graph, maybe yours looks like this. How many people's graph looks like this? Oh, nice. Okay, I just changed it to a standard window. What's the problem right now is your standard window on a calculator often goes from 10 to 10 and 10 to 10. If we look at the graph that we have here, if I want to see this, and my window is at 10 to 10 right now, can you see that that's what I'm seeing? So I need to go to my calculator and tell it it needs to look at a little bit more. How do you do that? Go back to your calculator. At the top, there's a window button. So if you click on the window, it says, what do you want your x min and your x max to be? What do you want your y min and your y max to be? Well, I want my x max to see up to 12.5 because that's what I graph. So maybe I'll go from negative 5 to 15. That'll show me a little bit to the left of my y-axis and a little bit to the right of where our graph was. And on our y-axis, well, we don't need to see a lot into the negatives. Maybe I'll just have a negative 2 so I can see that line at least, my x-axis. But our maximum was at 18.2, so I'm going to go up to 20 to make sure that I see it all. You can also set it however many of these tick marks you want. We had drawn them to be at 3.125 every single time. So if I go to my x scale, I can actually change it to 3.125 if I want those dash marks to match up exactly. Along my y-axis, it won't match up nicely, but maybe I'll go up by 5s. That just sets your scale. And now my graph looks very similar to the graph that I had drawn originally. Okay, I'll have a look at it. Again, make sure that you're in radians. The next thing we want to do is we've graphed that purple line at 14.5 to show the depth, the minimum depth of water that that ship needs. So on our calculator, we can go back to y equals, and in y2, we can write 14.5. That'll graph a horizontal line at 14.5. If we hit graph now, we can see that line. Now, the nice thing about technology is once we have both of those graphs in, your calculator has a bunch of things it can do. It's under calculations, which you have to push the second button and then the trace button. And one of the calculations it can do is find intersection points, number 5. So if I go down to number 5 and push enter, it says, what's your first curve? Well, I'm on the blue one, I can push enter. What's your second curve? I'm on the red one, I can push enter. What's your guess? I think they intersect right there. Okay, let's see if I'm right. And then it finds out where they intersect. It'll always find the point that's closest when it finds the intersection point. So we can now say that this first point is at 3.48. So I can label that right here, 3.48. What about my second point? Well, if I go back to my calculator and I go second, calculate, intersect, and I push enter 3 times again, it's going to keep finding the same one. because it always finds the one that it's closest to. So I can use my arrow keys to move my cursor closer. If you really want to be on the edge, you can say, is that close enough? You might be wrong and have to redo it, but there we go. Now for sure I'm closer to that other one. Push enter once, push enter twice, guess, and it finds the next one at 9.02. So for part B, for how many hours? If we go 9.02 minus 3.48, it's safe for 5.54 hours. So what did we have to do if we're going to use a graphing calculator to solve this? We had to know how to input it into our calculator. We had to be able to change the window so that we could see the same thing that we graphed. So your graphing skills are important because you need to know what you're looking for. You need to be able to graph it first by hand so you know what to set your window up when you want to use the technology. And then we could find the intersection points. Okay? This is not to say that this can't be done algebraically. So I'm going to show you algebraically how it's done as well. I've got it all typed up if you want to take a picture of it, because I won't give you enough time to write it down, or it'll be on the video after. So we're going to just go through how you would do it if you were solving it algebraically. So algebraically, since we know the depth of the water is 14.5 and we want to find out where those two graphs intersect, we could plug in 14.5 for the depth, and now we just have to solve for t. Well, what kind of equation is this? This is solving for something with a cos equation. How do you solve cos equations? Well, it would sure be a lot easier if I had the cos by itself. So I'm going to move the 13.7 over to the other side, divide by the negative 4.5, and that gets cos by itself. The other thing that this question has is a bunch of extra stuff inside of cos, which makes a horizontal stretch. How do we deal with that? Well, what we're going to do is we're temporarily going to say, if theta is equal to 0.16 pi times t, then my equation that looks complicated changes into something that looks easier to work with. Could you solve cos of theta equals 0.8 over negative 4.5? Yes, and you could use your grade 10 trig to do that. Well, grade 10 and grade 11. First of all, if you had cos theta equals 0.8 over negative 4.5, you would know from your cast rule that it has to be in quadrants 2 and quadrants 3. You would first find your reference angle, and whenever finding a reference angle, we always do cos inverse of the positive values. Since we're dealing in radians, my calculator is set in radians, and I find my reference angle is 1.392. We can now say, if I know my reference angle, and since cos is negative in quadrant 2 and quadrant 3, well, in quadrant 2, it would be pi minus my reference angle. Right? Draw a little picture here. Here's pi. Here's my angle in quadrant 2. My angle will be pi minus my reference angle. In quadrant 3, it would be pi plus my reference angle. If here's quadrant 3, there's my reference angle, and this is pi, my actual angle will be pi plus my reference angle. So we get two answers for theta. One answer in quadrant 2, one answer in quadrant 3. But now that you've got those answers in quadrant 2 and quadrant 3 and solve for theta, we look back and say, well, we're not actually wanting to solve for theta. What are we wanting to solve for? We're wanting to solve for time. And we made this temporary substitution right here that said theta is equal to 0.16 pi times time. We did that so our equation looked easier to work with. We could find our reference angle and solve for theta. Then after solving for theta, we can now go to quadrant 2 instead. And we had, in quadrant 2, we had theta equals 1.7495. So now we can substitute back, since theta was equal to this, we can substitute back 0.16 pi times t equals 1.7495. At this point, how do you solve for t? You'd have to divide by 0.16 pi. Okay? At this section, this is a very typical place where people make calculation errors. So I want you to type that into your calculator right now, because if you're going to make the error, I want you to make it right now so we can fix it so you don't make it again on quizzes or tests. So type that into your calculator. Push enter. Did you get 3.48? Anybody get 34.35? Okay, if you got 34.35, you did the common mistake, which looks like this. Here, I'm going to get 34.35 as well. So I had, oh, I can't remember the numbers, 1.7495. 1.7495 divided by 0.16 pi, and this gives me the wrong answer. Doesn't it look like I typed in everything right? Okay. What your calculator does in this situation is it does order of operations. It does 1.7495, then it says, you want me to divide by 0.16? It does that, and then it gets an answer and then says, oh, you want me to multiply by pi. But in reality here, we also want to divide by pi. So the best way to remedy this is if you have the newest version of the calculator, you write it with the fraction. Every time you can, use the fraction button, because then if you write it exactly like you saw it in the question, you'll get the right answer. Or, if you don't have that fraction button, whenever you're dividing by more than one thing, it would need to be in brackets. So if I had brackets in my denominator, I would have gotten the right answer. So these are important things to do because you don't want to lose marks on a test just because you typed something wrong into your calculator. So knowing how to use our calculator is important. That 3.48, all of that work is exactly the same as the 3.48 we found with our calculator the first time. Next, quadrant 3, do the same substitution, do the same dividing, and we get 9.02. So now we can write our statement. That ship is safe for 5.54 hours. Okay. So generally, you find in grade 12 pre-calculus that the question that we just did algebraically, they don't put ones with that much algebra on the exam. However, once you get to university, they're expecting you to be quite proficient with doing that every single time. So sort of like an expectation that's going forward to be able to solve those questions like that once you're in university. Okay. Question number 2. A Ferris wheel has a radius of 15 meters and rotates every 20 seconds. Yikes, is that a little fast? That'd be fun, that'd be exciting. Okay. We want to graph this function. One thing I find helpful with Ferris wheel problems is actually drawing out my Ferris wheel beside, label what I know. I know that the radius from here to here is 15 meters, 1 meter above the ground, so this distance right here is 1 meter. And then right beside it, I draw my graph. How high is it going to be here at the maximum? Where is my center line going to be? Center line is going to be at 16. How do you figure that out? The radius is 15 plus the 1 meter that it's off the ground. Perfect. And then what's your maximum going to be? Another 15 higher, 31. It rotates every 20 seconds. Does it make sense that if you get on at 1, 20 seconds later, you would be back at 1? If that is your period, you could divide that into 4 equal sections. Where are you going to be at 10 seconds? Halfway around, you'll be at the maximum. Where are you going to be at 5 seconds? The center line at 15 at the center line. Now, in a real Ferris wheel, it actually stops for passengers to get on, right? So we would have to take that into consideration. I don't know if they've ever had a Ferris wheel. They're like, okay, all right. You have to bail out the other side while other people are jumping in because it's not going to stop. I'll tell you a story. Now that we have the graph, we can estimate the height after 22 seconds. Well, an estimate just means if you looked at your graph, can you see that at 25, it would be back to the center line? So at 22 seconds, if I was estimating, it has to be somewhere between 1 and 16. According to my graph right now, I might estimate it at, what do you think? My lines look like they're going a little crooked here. This isn't necessarily the most accurate, but maybe I would estimate at 6. Now, if you wanted a more accurate graph, what we could do is we could put this into our graphing calculator. But in order to put it into our graphing calculator, we would need an equation. Okay? So what we're going to do is we've answered that estimate, we're going to answer the next estimate question, and then we're going to find out those answers exactly. So estimate what time you'll be 20 meters above the ground. Again, we could go to our graph, say if that's 1620 would be here, there'd be a point there, another one there. If I said this first estimate was at 6, what should I say my other estimate would be at? 14. It's symmetrical. So if one estimate was at 6, the other one should be at 14. Now, in order to find this exactly, we could use our graphing calculator, but if we're going to use our graphing calculator, we're going to need an equation for this. And getting our equation is pretty easy if we just think backwards from how we graph this. Your d values all use your center line. Your amplitude is from your center line to your maximum. Your b value can be figured out from your period, because your period is 2 pi over your b value. That means that your b value is 2 pi over your period. So in this case, my b value, well, my center line's at 16, my amplitude was 15, my b value will be 2 pi over 20, because my period was 20 seconds. And then when we go to write our equation, the c value is going to change whether you decide to write a sine graph or a cosine graph. So let's say I decide first that I want to write a sine graph. My amplitude is 15. My b value is 2 pi over 20. And my d value is plus 15. Where does a sine graph start? In the middle, going up. Where do we have in the middle going up? Right there. What kind of shift is that? 5 units to the right. So if I chose a sine graph, I would choose x minus 5. I could have also chosen a cos graph. The b value would stay the same. The a value stays the same. The center line stays the same. Where does a cos graph start? At a maximum. Where's my first maximum? 10 units to the right. So I could write x minus 10. Now I can go to my graphing calculator and enter in either of these. So let's say I choose the first one, 15 sine alpha y equals, to use my fraction button, 2 pi divided by 20, bracket x minus 5, whoops, bracket, to close that bracket, plus 16. If I want to see this, I look at the graph that I made. I need to go up till 20, at least 22 to see that, and my graph, my y values need to go up to 30, so I'm going to go to my window. I'm going to make my x max go up to 25, my scales going by 5s. And so I set my window so that I can see exactly the same graph that we had drawn. For calculation purposes, the first estimate we did was when it was at 22. If we go second calculate, the first one says value, you push enter on value, you can put any x value in. 22, what did we estimate it at? 6? Oh, 3.9. So we were a little bit off with our estimate. Look at my line. Oh, does seem to be going up. Maybe that was part of the problem. Had I graphed this more carefully on graph paper, my estimate probably would have been better. If I want to find out when it's at 20, on my graphing calculator, I can go and type in 20 into my second equation to draw a horizontal line at 20. Second calculate, where do they intersect? Enter, enter, enter. One is at 14.1. Oh, our estimate was pretty good there. And the other one (9.09). So our estimates were not too bad. Okay, so in the last 5 minutes, I would like you to do, in the try these on your own, try example 2, which is a Ferris wheel one, as well. Center line is 16. There we go. Oh, maybe our estimates were actually right. Or did I write 16 when I wrote it into the calculator? I think I might have.